Juniors, y'all are dismissed. If you don't have your candy, get your candy. Why do I have 2 stirs in my hand? Make sure everything's off, right? Right. All right. I'm good. You need me to put it back up for a second? I'll leave this up for just a second before I swap over. And this link is in your, yeah.
We do have to bring a look at these.
No, I just want the one that you got today. That's the only one I care about. The other one was for your note taking while you're doing it.
Thanks.
Yep. Okay, this link's in the Google Sheet. This is what you're working with. This is what you're graphing. All right? Do what? Yeah, it's already there. Link is already there, my friend. Okay. Hello, everyone. Oh, Lucy, you want your coins? Lucy. There you go, babe.
Also, I may be staying in.
You're fine. Take your time. You know, I'll do that all the time. You can sit with Eunice and start homework. That's what he does. Or you can just sit somewhere quietly, whatever works. All right, gang. Are we ready? Guys at the counter, y'all ready? All right. I like this particular lesson because the aesthetic is all yummy looking, delicious treats like this milkshake and whatever else. Yeah, you know, I really enjoy the aesthetic. If you're going to leave hungry, I apologize ahead of time. Who does?
History teacher.
Mm-hmm.
Could she also learn food history?
Oh, fun. Oh my. Okay, yeah, that would be, yeah, you'd leave hungry every time. There's this place in Virginia Beach that I visited, kind of happened upon it by accident. But it was called the Yard Milkshake Bar. And they give you like, it's a glass like that kind of, but the milkshakes are ridiculous. Like one of them has like a brownie on top, another one has like a slice of cake. Like they're ridiculous milkshakes. I'm there for it. All about. All right, so opportunity for, actually it should, I didn't change the top, but this should say extra credit. Opportunity for extra. No piano. Extra credit on unit test 7. I meant to change that. So there are going to be some really, really bad science jokes, puns, and riddles dispersed throughout the lesson. Pick one that makes you laugh, snort, roll your eyes, or facepalm. Either it's funny or it's so awful you can't believe I made you endure it. And make a meme or a drawing to represent your pick. Don't copy what I give you. And then post it in the forum under the heading memes, which is already there. That should say 2024, 2025 chemistry. I just forgot to change it from the last time I taught this. But it's there under, it's not under labs. Be sure that when you're in the forum, you're under the one that says chemistry all. Go there, post your meme. I'll add 2 points to your unit 7 test. Yes.
7 what we just did, or what was
6 is what you just did. 7 is where you're headed. So this gives you an opportunity. Yes. Sure. I don't care. I use it all the time. All right. So make you a meme for one of these ridiculous jokes. They're everywhere. I apologize ahead of time, but it keeps people engaged. So mixtures. What's a mixture? What are the types of mixtures? So we're going to use this as a great example as a mixture to begin with. Keep this image in your head as we're talking, all of those different sprinkles, okay? You can see that there are little star-shaped ones. There's Jimmy's, there's Dragees, there's big fat ones, there's these little guys, nonpareils, all kinds of yummies in there. So what did Michael Jackson say when he found 2 helium atoms? He said, hee hee. Whoop, there he goes. Hee hee. Yeah, okay, everybody knows that one. Hee hee. Oh no, it's really stupid, but you're paying attention. All right, mixtures. Ah, who likes this cereal? Guilty pleasure. Lucky Charms? Guilty pleasure? Guilty pleasure. Oh, it is for me. I might buy it once a year around St. Patrick's Day, just like I buy Blueberry and Frankenberry once a year at Halloween. You'll have to have the Blueberry and the Frankenberry, like that's a must. So anyway, they've definitely increased their number of marshmallows. When I was a kid, it was like pink hearts, orange stars, green clovers, yellow moons, and blue diamonds. And then I remember when they added the purple horseshoes, it was a big deal. And now they've got like rainbows and all kinds of things in there. So they what? Oh, I never had it with an hourglass. All right, well, it's all supposed to be things that you wish on or that are lucky, I guess. I don't know. So a mixture is a substance made by combining 2 or more different materials in such a way that no chemical reaction occurs. And a mixture can usually be separated back to what? Yes. Yes, to its original components or its constituent parts, however you want to say that. Yes. Could you separate this cereal back into, little oat cereal pieces and marshmallows? Yes, you could. And would it be difficult? I don't think this would be too difficult. Yeah, I've seen that.
It'd take a lot of time.
You can go on Amazon and buy like giant mags of those dehydrated marshmallows that like come in the cocoa mix. Yeah, yeah. So I was going to make a joke about sodium and hydrogen, but no. It's bad, right? All right, types of mixtures. So we have this type of mixture where particles are evenly distributed and not easily separated. And then we have this type of mixture where your particles are easily separated. What are these? All right, Xander. Uh-huh. Getting there, not quite. Jordan?
Homogeneous.
Okay. There you go. All right, so these words, yes. So you're going to see, so let me just tell you, depending on who's speaking, you may hear it pronounced homogeneous or homogeneous. And when you see heterogeneous or heterogeneous, depending on who taught you, right? I kind of use them both. Now, I used to be all homogeneous, heterogeneous, but now because like Professor Dave is homogeneous and heterogeneous, he kind of got into my head. So I'll use them kind of interchangeably, and a lot of people will, but you'll hear both. You will hear both. So if this is salt, we don't know what it is, but let's just say it's salt that's being dissolved into this glass of water. The particles are going to be evenly separated. And well, let's just say sugar even. Okay, let's pretend it's sugar because that's tastier. Okay, sugar. The particles are going to be evenly separated. You're going to have sugar molecules evenly dispersed throughout the water, correct? We all agree? It's a mixture though, which means that it can be separated into its constituent parts by a physical process. What would you do to get the sugar out of the water?
Boil.
Boil it or evaporate it, right? Basically, you need to have a phase change situation going on to make this easier for you. Not that off. There we go. So, but you could separate it out, right? You absolutely could. And how about the berries? How would you separate that? Yeah, just pick them apart, right? That's not hard. Anybody have a favorite berry in this situation here? What you like? Raspberries? You got a backyard full of blackberries for somebody who prefers the raspberry. Yeah. I got raspberries. What do you think?
Do I have to pick a berry in the bowl?
Do what?
Do I have to pick a berry in the bowl?
No, do you have another one you like?
Bananas.
Oh, technically a berry. Yes, very yummy. Yum. There you go.
That's so weird.
Yeah, they are.
Yeah, it's like tomatoes. Tomato is a fruit. And you're like, huh? All kinds of fun things like that. My dad called me the other day. He always thinks he's gonna stump me. And he's like, hey, I got one for you. I'm like, okay. And he said, what kind of fruit has the seed on the outside? I said, strawberry. He said, yeah, you know that already. And I said, yeah. And then what did he say after that? It was something equally like, I don't know. It was something equally weird. And I immediately came back and he was like, yeah, I guess you knew that already too. I'm like, sorry. Heard this one 400 times. All right. So, types of heterogeneous mixtures. So, heterogeneous particles are easily separated. So, we have types. We have a suspension. Can somebody define suspension for me? What's a suspension? Caitlin. Yeah, so they're pretty evenly dispersed, but they're solid particles. And here's the trick. They're sufficiently large for sedimentation. So does anybody know what that is in that class? Those aren't ants.
Chia seeds.
Those are chia seeds, right? And chia seeds make a great suspension because when you get chia seeds wet, they have like a coating on the outside of the seed that produces like a gel, right? And then they get kind of slimy, which is how you spread. Anybody have a chia pet? Oh, come on. Nobody has a chia pet? Oh, we had one. They're fun. It's like a little terracotta creature or whatever. Actually, the one we had, somebody got as a joke, and it was Donald Trump's head, which is it was just funny. But you soak it in water, and the terracotta absorbs the water, and then you soak the seeds in water, and they get like a jelly kind of around them, and like frog eggs, kind of. And then you spread it all over, like in this case, Donald Trump's head, and then he grew chia sprouts. It was very amusing. But it used to just be like a little animal.
I subscribe to this cosmetology school, and sometimes they turn their mannequin heads into like different things, and they turned their mannequin head into a chia pet,
I love it.
and it looked really gross.
I love it. Yeah, it does get like like green Bob Ross hair. Yes, like a afro hair.
They make a Bob
like that.
Ross chia pet.
Yes, they do, and I want it. so anyway, those are chia seeds. But another great example of a suspension is if you were to go out down to the Chattahoochee after it rains, when the water is that lovely red clay color, right? And scoop up a bottle of it and bring it up here and put it on the counter and leave it. Over time, your water would be nice and clear, and at the bottom would be all your silt and what we call bed load, because a flowing water is a suspension. It has particles in it that are moving throughout it, right? And you would see some of that bed load settle down into the bottom, and you'd see the silt down there. So another thing you can do is take a bottle full of glitter and water, shake it up. What happens over time? Yeah, it's going to settle down to the bottom. So a suspension has particles that are sufficiently large enough for sedimentation, which means they will settle to the bottom like sediment. If I were a DJ, my name would be DJ Enzyme, because I'm always breaking it down. We're going to talk a little more about enzymes next quarter, but these are catalysts. These are catalysts found in nature, and a catalyst is going to lower your activation energy, so it helps a reaction go forward faster, typically. So yes, and it also breaks down proteins and things. So there you go. If I were a DJ, I'd be DJ Enzyme. Types of heterogeneous mixtures. Another type would be a colloid. Who can define a colloid for me? Caitlin.
A mixture consisting of tiny particles that are intermediate in size between those in solutions and suspensions.
There you go.
Are suspended in a liquid, solid, or gas.
Yes, yes. Do you have anything to add?
That's the book. That was what the book said. I did not understand that at all. So I have a different.
Okay, what did you get?
Mixture comprised of a solid broken up into microscopic particles in a liquid.
There you go. Yeah. So basically, this is something that also will separate to some degree with time. But it's not like they're big particles that are going to be like a sediment, like in the case of silt and water from the river that's going to settle out. In this case, they're much, much smaller particles. So a great example is milk. So has anybody ever had non-homogenized milk? You've had it? Like on a farm, or did you buy it at the store? On a farm? Yep. Have you had it? Unfortunately. Okay. So when you go to the store and you buy milk, most of you are buying homogenized milk. If you don't have to shake your big jug of milk before you drink it, it's been homogenized. And I'm going to show you in a minute how they do that. But non-homogenized milk is how milk naturally exists. Anybody ever babysit? Like, no, anybody ever babysit like a breastfed baby? So human milk does the same thing that cow milk does. If you leave it long enough, it will separate into the whey, and then you'll see the cream rise to the top. That's why they say that the cream, you know, we're talking about like the cream of a population, or the cream rises to the top. That's why, because it's a lipid, it's less dense than the water, which is the main constituent part of the whey, and the cream will rise up.
My friend who's been to Disney a lot,
Mm-hmm.
they found abandoned like breast milk in the fridge, and
Yeah.
it was like really weird looking.
Yeah, it separates out. Mm-hmm. It'll separate out. You get a nice thick layer of milk fat on top. And actually, the humans are fascinating. Like you can, if you have a breastfed baby in your life, that you can watch the bottles that get pumped, but you'll see that based on how much growth that baby needs, how much fat that baby needs, the mom will produce more fat. So you'll see more of the cream on top. The ratio of cream to whey is not always the same. And actually the way it works is like there's 4 milk kind milk, and the same kind of thing happens with cows, but with mammals in general. What you get at first is the fluid that hydrates the baby, and then the fats and all of that stuff come later. So that's why it's really important to make sure you get like a full feeding for any baby that's not drinking like a formula. Otherwise they don't get all the components they need because they come out in a different order. Fascinating, right? Pretty interesting. All right, so great example of a colloid is milk. And it also undergoes Tyndall effect, which we'll talk about. If you're not part of the solution, no, you're part of the precipitate. There you go. Okay, yeah, these are bad. I told you, some of these were bad. You're part of the precipitate. Okay, what's homogenized milk? All right, we were just talking about how most of the milk you drink is homogenized. Well, how do they do that? What's the process? Hello. Yay! So Organic Valley, you probably recognize this brand. You can get it at Publix. I think even Walmart has it. Target. Maybe sometime today. Come on, food scientist, where are you? What's happening? Boy, here we go.
You ever wonder
No.
for
What?
what exactly is homogenized milk? Well, you're not alone.
Dear Organic Valley, I noticed that you have homogenized and non-homogenized. What's the difference? Great question. Here's one of our food scientists with the answer.
I'm Emma Grindy, a product development food technologist, and I've been with Organic Value for 5 years. Homogenization is simply the process of breaking down fat molecules so the milk has a smooth and even consistency. Homogenization doesn't involve additives or chemicals, and homogenization doesn't alter the nutritional benefits of drinking milk. In its natural state, all raw milk is composed of protein, water, and butterfat. Left alone, the fat will rise to the top, creating an obvious layer of cream. This is where we get the saying, only the cream rises to the top. When milk is homogenized, it's heated, agitated, and passed through a valve at high pressure. This physical process changes the fat molecules so they are the same size and density as the rest of the milk. The result? Homogenized milk is always smooth and consistent.
That's really all there is to it. But if you would like to try milk with the cream on top, Organic Valley makes several non-homogenized dairy
So
products.
if you want to try non-homogenized,
Cream on.
you can go get it at Publix or whatever. You can do it. So we have the Tyndall effect. This is something that colloids do. They produce the Tyndall effect. So the Tyndall effect says colloids are often confused with homogeneous solutions because the individual dispersed particles of a colloid cannot be seen. You can't see the individual particles in milk, can you? No, but you could see those chia seeds, right? So when light is passed through a true solution, the dissolved particles are too small to deflect the light. However, the dispersed particles of a colloid, being larger, do deflect the light. This figure's actually above, not below here. The Tyndall effect is the scattering of visible light by colloidal particles. You have undoubtedly seen a light beam as it passes through fog or smoke, or a scattering of dust particles suspended in the air. All three are examples of colloids. Suspensions may scatter light, but if the number of suspended particles is sufficiently large, the suspension may simply be opaque and the light scattering will not occur. So this shows you kind of exactly how that works and what's happening there. If it'll play, I don't know why everything is laggy today.
Topic, Tyndall effect. Why does the sky appear blue? Don't know the answer? No worries. We shall find the solution.
Hmm. Hmm.
He's having a bad day at the beach.
Beautiful rainbow. Have you ever wondered how it is formed? A rainbow is formed when raindrops split sunlight into different colors. Sunlight or white light consists of many colors. However, only a few of them are visible to us. A band of these visible colors is called a visible spectrum. When we see a rainbow, our brain and eyes distinguish the visible spectrum into 7 main colors, namely red, orange, yellow, green, blue, indigo, and violet.
Evil son.
Oh.
I'm not sure what's happening there, but that part's not. It's kind of weird. It does get back to the
Notice
science
that
though.
the size of the balls increased? Yes, you guessed right. The balls represent the different colors of a rainbow in increasing order of their wavelengths. Wavelength is the distance between consecutive crests or consecutive troughs in a wave. In a rainbow, as we move from violet to red, the wavelength of colors increases. Violet has the shortest wavelength, while red has the longest wavelength. Do you think that our eyes have a natural inclination toward blue as compared to violet? Yes, this is one of the reasons why our sky appears blue and not violet. To understand this, first, let us study about Tyndall effect. Tyndall effect is a phenomenon in which a beam of light scatters on striking the particles present in its path. This scattering of light is responsible for the blue color of the sky. We know that our atmosphere primarily consists of oxygen and nitrogen particles, along with dust, smoke, and other particles in comparatively smaller proportions. The size of these particles in the atmosphere is responsible for the color of scattered light. When the sunlight strikes particles of dust, smoke, etc., which are bigger than the wavelength of sunlight, all the colors of sunlight are equally scattered. As a result, the scattered light appears white. However, when the sunlight strikes particles of oxygen and nitrogen, which are smaller than the wavelength of sunlight, the colors of sunlight having shorter wavelengths, that is, blue and violet, are much more scattered than colors having longer wavelengths. But our eyes are much more sensitive to blue color as compared to violet. Hence, the sky appears blue to us.
Oh.
I don't know why we're all laughing at his demise, but hey, so
I saw someone put
I don't know, the parts in between the weirdness were good, but sometimes you gotta endure the weirdness. He's an old man laughing.
this one old man laughing. and
So
then-
our types of colloids. All right, so you've got classes of colloids, which are solid and gel, solid aerosols, solid emulsions, liquid aerosols, and foams. And this tells you whether it is, in this case, it's going to be dispersed as a solid, a liquid, and a gas. And this gives you an idea of what the medium is. So liquid, gas, solid, liquid, gas, solid, liquid. And examples: jellies, paint, smoke, dust in the air, cheese, butter. These are all colloids. Milk, mayonnaise, fog, mist, clouds, aerosol spray, marshmallow, whipped cream, shaving cream. All examples of colloids. So how do you separate a colloid? Okay. If you've ever been to the doctor, you've probably had this done, or at least this is how they used to do it. Now it's a little different. They use cool little machines, but this is still cool. Look right there in micro hematocrit centrifuge. You can probably already tell what's going to happen based on that word. Micro is small. Hema is blood. Yes, microhematocrit. So we are taking small blood samples and putting them in a centrifuge. Okay. So if you've ever had this done, this is how they used to do it. Now they tend to, sometimes they still do it this way. Sometimes they put a little thing there, like a little, what is it called? I don't even know. This right here is called a capillary tube. You ever seen this? And there's your capillary action. That's your water. Those are your hydrogen bonds at work. Has the blood go up the tube. So they put a little bit of putty on the end. That just seals the end. And then they're going to put it in the centrifuge. Which is going to spin it. So it'll force the more dense particles to the bottom and the less dense particles to the top. And after a minute, when they take it out, it has separated the colloid, which was blood in this case, right? You can see that's the plasma, that kind of yellowish is the plasma. You got your red blood cells at the bottom. And then these machines have this built-in little scale for measuring. So that right there is your hematocrit. They're going to measure the distance right there. That's how many red blood cells you have. And then there's your plasma and your white blood cells at the bottom of the plasma. And if you ever heard, like, what is your hemoglobin? How much iron do you have? That's exactly how they figure out how much iron is in your blood, because you need hemoglobin in your red blood cells, and your number of red blood cells can be impacted. So what kind of bears are soluble in water, people? Polar bears. Oh, bears are insoluble in water. That's easy for you to say. And we'll talk a little more about why that's a thing when we start talking about solubility. Basically, like dissolves like. So polar dissolves polar, non-polar dissolves non-polar. Anybody ever worn like grease paint or theater makeup or Halloween makeup that's oil-based, not water-based? You got to take it off with like cold cream or baby oil or something. You have to remove it with another lipid. It's not going to come off with water. It's going to just, the water's just going to repel, right? But we've talked before about, like, anybody ever wash a greasy pan before? When you add the dish soap, that's the only way you're going to get the grease out, is by the dish soap, right? Well, why does that work? Same reason they use it on like ducks when there's oil spills and stuff. And it's because the dish soap itself is a surfactant. It has a polar end and a non-polar end. So the non-polar end will attach itself to the lipid or the oil or the grease, and the polar end of the molecule will attach itself to the water. So when you wash it away, the water will take the grease with it. Otherwise, they're not going to mix, right? So it doesn't mix them, it just attaches them to another molecule, one on each end. And you have a natural surfactant in your body. Does anybody know what I'm talking about? You know?
What? What?
Do you know? Some in there. Probably the most impactful one is in your lungs. You have surfactant in your lungs, and here's why. You ever have that thing? You've probably seen it. Well, you know the thing where sometimes my lips get stuck on my teeth with dogs, you know, where their lips are just slightly damp and they stick to their teeth because their teeth are slightly damp, or sometimes you may have had your lips kind of stick together a little bit when they're just barely wet. Okay, well, the inside of your lungs, you have all those little alveoli, all those little air sacs, and when you exhale, it's collapsing. And if you didn't have a surfactant in there, surfactants tend to be slippery. Is dish soap slippery? Nice and slippery, right? So, you have slippery surfactant in your lungs so that when you exhale, your little alveoli and air patches don't just stick together, making it impossible for you to inhale again. But surfactant doesn't develop in your lungs until the end of fetal development. So preemies that are born really early sometimes don't have enough surfactant. And in the past, they would have just died. They would have suffocated because their lungs would have collapsed as they tried to breathe. But now what we have some things we can do to kind of speed up their own production of surfactant. But they tend to put them on ventilators. And if you've ever seen a video or in person of a tiny preemie on a ventilator, it doesn't breathe like you and I do. It doesn't breathe like normal in and out. It breathes rapidly like this. And it never allows the lungs to completely collapse. It's just constantly puffing air in and out. And that's how they stay oxygenated, because otherwise their lungs, if they allowed to collapse entirely, they're not going to open back up. So you've got surfactant in you, which means it has a polar end and a non-polar end, and it tends to be nice and slippery. So types of homogeneous. So we did heterogeneous. Now let's do homogeneous or homogeneous mixtures. A solution. What do you suppose that solution is? Scott, James?
Water and
Yeah, water and carbon dioxide. Look like soda water, club soda, seltzer, Sprite. Could be any of those things, right? Somebody's White Claw, I don't know. Basically, you've got a gas that has now been dissolved in solution into a liquid, but you can also dissolve solids into liquids and liquids into liquids. So a homogeneous mixture is composed of two or more substances, a solute, which is dissolved, and a solvent, which does the dissolving. What's the solvent in this picture?
The water?
The water. And what's the solute? The carbon dioxide in this time. Yeah. Yep. Carbon dioxide. So what element's name is derived from a Norse god? This one's more of a do you know it trivia. Anybody know? Do you know it?
Is it like thorium?
Yeah, thorium. There you go. Yeah. There you go. Thorium. It's cute. No. All right. So here are some examples of homogeneous, heterogeneous, and other heterogeneous. So heterogeneous broken down into colloid and suspension, and solution broken down is just homogeneous, right? So it gives you an idea of the particle size. So if you look here, particle size in your solution is going to be like 0.01 to 1 nanometers. We're talking tiny. Whereas if you get all the way over here to suspensions, you've got your bigger particles, right? That you can sometimes even see. And those are going to be over 1,000 nanometers. So larger aggregates, right? And then solutions do not separate on standing. Colloids typically don't separate on standing, though some of what goes on in milk will separate. And suspensions, the particles are going to settle out. In this case, though, the particles that settle out are going to fall down, whereas with milk, you're going to see the denser particles force the less dense cream to the top, right? Cannot be separated by filtration. You can't separate a solution by filtration. But colloids typically not, but you can filter out for suspensions. Anybody ever had like a life straw? Yeah, they're like these little it's a water bottle with like a straw that goes down to that has filters on it, so you can literally like scoop up river water and drink it, and it's filtering out all of the larger particles and hopefully the microbes. That's your idea, right? Hopefully the microbes. And solutions don't scatter light, but colloids do. and suspensions can, or they can be opaque. So I heard that oxygen and magnesium were going out, and I was like, OMG. That's Liam's favorite so far, right? Liam, you love that one. OMG. Okay, yeah. But everybody's paying attention for a minute. There you go. Suspension, solution, or colloid? Let's take some votes and see. All right, which is it? Suspension, solution, or colloid? Who votes suspension? Glitter in water. Who votes solution for glitter in water? How about colloid? So this one's going to be a suspension. It's going to settle out on its own. Those particles over time, you can even see them in the picture. They settle down to the bottom. Anybody ever make one of these when you're little? What do they call them? They call them something. It's like
Snuggle.
they're what? No, they're like sometimes you make them for little kids that have trouble calming themselves down, and like they just sit and watch the particles settle and they learn to. Yeah, it's kind of like, there's a word for it though, I can't remember, but the idea is that it's something for them to watch. And yeah, kind of like it. Yeah, yeah, it helps settle people down.
All the water time.
Yeah. How about this? Suspension, solution, or colloid? So who votes suspension for a Jello mold? How about a solution? How about a colloid? Yeah. So technically we're talking about a colloid here. And then air, suspension, solution, or colloid. Who says it's a suspension? How about a solution? How about a colloid? It's going to be a solution. So you can't filter out. There are ways to separate the components of air, but it's not going to settle. Their parts aren't going to settle on their own, right? And the particles in the air can cause some of what we're talking about, the Tyndall effect, but the air itself is a solution. Now, solutions are not always liquids, right? They can be gases, like in this case, and they can also be solids. So like examples of solutions that are solids are like alloys. So steel, brass, these are solutions. And when we put metals together like that, we call them alloys, but they're technically just a type of solution. All right. Solids and solvents. So we have what is dissolved and what does the dissolving. So again, what is dissolved? The solute. And what does the dissolving? The solvent. So if that's sugar, will it dissolve in water? Yes, it will. Okay. Now here's the thing. We'll talk about this more in a minute. If that's salt, will it dissolve in water? Yes. Okay. Here's the difference. If you're going to put your ionic compound, like your salt, in the water, it's going to dissociate into its ions, right? So you're going to have sodium ions and chloride ions floating around in your water. But if you put the sugar in the water, is it going to disassociate into any constituent parts of that molecule? No, the molecule is going to stay the molecule. So what's happening when you're dissolving covalently bonded molecular substances is you're actually just breaking the intermolecular bonds, you're not breaking down the compound itself. You're just breaking the intermolecular bonds that hold those molecules together. So here's dissolving. So dissolution occurs when a solute breaks up from larger particles into much smaller groups or individual molecules. This breakup is caused by coming into contact with what? What do you have to come in contact with to dissolve? Yeah, your solvent. Yeah, there you go. All right, so you put the candy cane in water, will it dissolve? Yeah, gonna turn your water like a weird pink color. Yeah. Cotton candy? Yeah, that too. Yep. We'll actually talk about that one in a minute. So now we're going to talk about concentration for a minute. So concentration of a solution is the quantity of what contained. Yeah, your quantity of your solute that's contained in a particular quantity of what? Solvent. Yes. Okay. So sometimes concentration is obvious. In this case, if you're dealing with something that has a color, it's real obvious. But today, if you had different concentrations of your sodium chloride solution with water, you probably wouldn't have been able to tell by looking at it necessarily which was more concentrated. concentration can affect density, it can affect color, it can affect how well light passes through, depending on what you're dealing with, right? So next week in lab, we're gonna have some demos. And one of them we did at the very beginning of the year, we did the density column. Do you remember the density column with the different concentrations of sucrose? So we're gonna do that again, but you guys are gonna get to be the ones to pour. So we're gonna pour different concentrations of sucrose solution, so just sugar and water, and we're gonna layer them up in a graduated cylinder. And it's really cool because you'll see them separate out based on the density, and the density is due to the concentration. So we have one that's 90%, 80, 70, 60, 50, that kind of thing. Then we also are going to do a demo with a super saturated or highly concentrated solution of sodium acetate trihydrate. Has anybody ever used that before? Sometimes it's called hot ice. People call it hot ice because it looks like ice and it's exothermic. You can actually feel the heat. Yeah, you can do cool stuff with it. So next week I'm gonna do some demos with that. You guys are gonna get a chance to see it, but you can actually watch something go from a solution to a crystalline type of solid in a matter of like seconds. It's cool. Yeah, all you have to do is microwave it. Literally, or heat it up. You can microwave it or you can heat it on the hot plate and you can use it again and again. And the stuff I made 4 years ago. It still works fine. Like you just keep using it. I don't know. Maybe there's a lot of videos of it on YouTube, but it's interesting. Like, you ever go to the beach, and my uncles used to call them drizzle castles, but I don't know what other people call them, but you get a bucket full of sandy water and then you drip it like this through your fingers and it drip, 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 and it makes like this little drippy castle, right? Those are fun. It's like that, but you're using it with what looks like a clear liquid, and then suddenly it just starts to like stack up. It makes like a stalagmite of like a white crystalline solid. It's fun. It's fun. So we'll be doing that next week. So what do you do with a dead chemist? Anybody know? Nobody knows what you do. You bury him. Oh, yeah, that's a good one. That's a solid one. You bury him. All right, molarity. We have talked about moles, molar mass, all that stuff. Molarity. Okay, molarity is really important in chemistry. So it's a way of describing concentration. And it's most useful for calculations when you're doing stoichiometry, for reactions with solutions. So the molarity is defined as the number of moles of solute present in exactly 1 liter of solution. So it's moles per liter. And it is equivalent, it is equivalently the number of millimoles of solute present in exactly 1 milliliter, obviously, because if you're a liter, if it's moles per liter, then it's millimoles per milliliter, right? So all of the solutions that we use in lab have a molarity marking on their label. So we have like everything from like 0.1 molar hydrochloric acid or 0.01 molar, I think, and then we have 1 molar. So the higher your molarity, the higher your concentration. And there's a great app, actually. If you are ever curious, there's a fabulous app, and it's maybe I don't know where I put it. It's like in the lab or something like that, but it helps you, like you can say, I need to make a 2.0 molar solution, aqueous solution of whatever, and it'll do the calculating for you, so you don't have to like go pulling AMU and all this other information to get it. So it can be very helpful, but that's molarity. And so here's how you do it. It's moles of solute to liters of solution, or millimoles of solute to milliliters of solution, right? Makes perfect sense. And the units of molarity are therefore moles per liter of solution, or mole per liter, and it's abbreviated as MM. Sometimes you're just going to see it as M. So an aqueous solution that contains 1 mole, or 342 grams of sucrose in enough water to give a final volume of 1 liter has a sucrose concentration of 1 mole per liter, or 1 molar. That's your molarity. You'll see it as just a big M, 1 molar, or 1 molarity. So that's just a way to designate concentration in a more specific. You can do it as percentage or molarity, but molarity is often used in lab. So our universal solvent is water. Why?
But
Yeah, yeah. What else? Yeah, we have a lot of water, and it does a good job of dissolving a lot of things. Over time, it'll dissolve a whole lot of stuff. Obviously, there are things that it won't dissolve, but there are certain things that it will, and a lot of things that it will. So dissolving ionic and molecular solids. All right, so this right here is a compound which exists as solid ionic crystals dissolved in water as ions. Most of them are highly soluble in water, and the positive and negative ions spread apart and are surrounded by water. Anybody want to guess what that substance is? Do you know, Lucas? Pink Himalayan salt. He got it on the first try. That is pink Himalayan salt. And then this one here, dissolving a molecular solid requires breaking only the weak intermolecular forces, not covalent bonds that actually hold the individual molecules together. So molecular solids are relatively soluble in water. Liam, what's that?
Cotton candy.
That is cotton candy. I mean, does anybody have a favorite cotton candy flavor? What do you like? The blue?
They had the pink one and the blue one.
Yeah?
Yeah.
The pickle? Okay, I was gonna ask if anybody had tried the pickle. Okay, so you have tried the pickle. Is it good? It's good?
It's the best one.
It's
Really?
not like, wow, that's amazing, but no cotton candy. It's like, wow, that's amazing.
I love all cotton candy. So it's so delicious.
Pickle tastes exactly like a
just
pickle.
kind of
Does it for real? I'm always worried it's gonna be like, no, that's
No, it
fake
tastes like
pickle.
no, it's a pickle.
Cool.
It's so good.
Drew's Easter basket. Was it Easter basket last year? Or was it Valentine's Day? You had like 6 different flavors of cotton candy, remember? There was like grape, watermelon, orange, green apple. It was fun. It was like all the different flavors. They were little containers, but it was really good. We tried them all. So yeah, like we said before, if you've got an ionic compound, it's going to disassociate into its ions. If you put that pink Himalayan salt in water, it's going to dissolve into solution. You will no longer see it, but it's broken down the actual compound into its constituent ions. Whereas if you've got cotton candy and you dunk it in the water, it's going to break down so that all of the sucrose molecules are on their own, right? And they're mixed into the solution, but the sucrose molecules still are the sucrose molecules. They're not disassociating into ions because that's not what covalent or molecular compounds do, right? So, anybody ever had the cotton candy in your drink? You ever done the drink with the cotton candy in it before? Sometimes they do that at weddings and stuff. They'll put it in champagne. They'll put like a blob of cotton candy on top of champagne. Yeah, and it just dissolves into it changes the color of the drink. Quite yummy, actually.
Sounds cool.
It is cool. Yeah, yeah. I've done it for drinks before. Like I've done it for Christmas for drinks or whatever before, like in the pub when I'm having a party. But you can do it on your like soda or whatever too, and it'll change the flavor and color of your soda. It's kind of fun. So yeah. So it's different dissolving for different types of solids. Why are chemists great for solving problems? They have all the solutions. It's so funny. All right, so what's in your binder? Let's see if we can go over some of jumping stuff. All right. Solution. Some of these we've already given, but let's let other people go. Colin, what you get for solution?
mixture of 2 or more substances uniformly dispersed throughout.
There you go. So homogeneous mixture composed of 2 or more substances. In such a mixture, a solute is a substance dissolved in another substance known as a solvent. And yes, even very evenly dispersed. Suspension, Jordan? Yep, a heterogeneous mixture that contains solid particles sufficiently large for sedimentation. It's evenly dispersed, but they're large enough particles that they're going to become sediment at some point. All right, and solvent, Colin?
Primary ingredient in a solution.
Primary ingredient in a solution, that's a good one. A substance, oh, do you have another one for that? No? So a substance, ordinarily a liquid, but not always, in which other materials dissolve to form a solution is the solvent. Solvent does the dissolving, right? WD-40. People tend to think of it as a lubricant, right? They're going to squirt it on their door, you know, their keys, locks when they get stuck or whatever. Technically, it's a solvent, and my husband will die on that hill because, you know, we've had some sticky doors lately. Y'all know some of you couldn't get in. Poor Jordan was stuck outside. It happens. Like the doors gotten really cold and then they just didn't work. And I was like, well, do we have any WD-40? He's like, it's a solvent. It's not a lubricant. I'm like, fine, I give up. Like I tried before. He actually bought like special silicone lubricant so that we don't have to use a solvent in the lot. But all right, so solute definition, Xander?
A component that is dissolved in solvent.
Right, so the substance that is dissolved in a solution, dissolved by the solvent in the solution. All right, colloid. Who's got colloid? Colin.
A mixture consisting of tiny particles that are dispersed evenly.
Yes. Yes, dispersed evenly, but don't settle out. And this is Tyndall effect. It will scatter light. Typically, a colloid will scatter light. Sometimes suspensions may be even opaque, depending on how big the particles are. But in a colloid, the particles are just big enough to scatter the light. All right, concentration, Colin.
Ratio of solid to solvent.
Right, the amount of a substance in a defined space or volume, the ratio of a solution to either solvent or total solution. So solvent, you can do concentration as the ratio of solute to solvent or the ratio of solute to the whole solution. You can do them either way. And then we're going to typically define that by molarity. Does somebody have molarity? Jordan.
Unit for concentration for mole of solid per liter of solution.
There you go. So a number of moles per per liter of solution. Moles per liter. Okay. How many ppm is what?
Parts per million?
Parts per million. Are there in a sample of tap water with a mass of 750 grams containing 2.2 grams of what's Hg? What's Hg? Mercury. Do you want mercury in your water?
No.
Why not?
It's poisonous.
It's a neurotoxin, right? Yes, it's poisonous to your nervous system in particular. Is there mercury often in tap water?
Sometimes.
Sometimes there can be, but is there a level of mercury that is safe versus a level that's unsafe?
Yes.
Yeah. Same thing with fish. Okay, you get mercury in the water, mercury gets out into the water, and the little tiny plankton and whatever, they absorb the mercury. Okay, and then your little fish eat your little plankton, right? So now your little fish have kind of an exponential amount of mercury based on the number of little plankton they ate. Everybody following me?
Yeah.
Now your bigger fish eat your medium-sized fish eat your little fish. Now they have an exponential amount of mercury as compared to the tiny little creatures, the little plankton. So your little plankton have mercury, and then if you eat 2 plankton and you're a fish, now you've got twice as much mercury. And if you're a medium-sized fish and you eat 2 little fish, now you have 4 times as much mercury. How about big fish? What's a big fish that we commonly eat?
Tuna.
Tuna's the one. Yep. You have another one? Catfish are big. Tuna are huge. Tuna are alike. Anybody ever seen a tuna?
Oh, they're massive.
Does anybody like tuna? I love tuna fish sandwich. It's like one of my favorites. I'm not big on like the tuna steak or the sashimi or the whatever. I love a tuna salad sandwich though. That's one of my absolute favorites. I don't like the weird pickles or anything strange in it like that. Just give me celery and red onion and I'm happy. But yes, tuna are big fish. They eat lots of medium sized and small fish. So the level of mercury in tuna is way higher than the level of mercury in a little itty bitty fish, like a sardine, right? So that's one of those things that is constantly tested to see whether or not it's safe. So if it's wild tuna, they're always making sure that the levels of mercury are safe before they stick it in a can and give it to you. But there's like people, they used to put mercury in vaccines to kind of like stabilize. It was like a preservative type of situation. They don't do it anymore, but they did do it at one point, and it was a tiny bit. But there were so many people that like freaked out about it because it's not good, right? It's not good, obviously. And there were people that was concerned that it was being linked to developmental disorders and all this other business. But then there are also studies that say there's more mercury in a tuna fish sandwich than in a vaccine. And I eat a lot of tuna fish sandwiches. So maybe that explains some things. But yeah, it's entirely possible. But yeah, so as far as this problem goes, how do we work this out? Okay, so yes,
Regarding point.
Yeah.
In the binder, instead of mercury, it says OG mercury.
oh, write it down.
2.2 grams OG.
Ah, well, write it down. So your parts per million is your measurement of concentration of solution, ppm. For very dilute solutions, it's weight divided by weight, or weight divided by volume. Concentrations are sometimes expressed as parts per million. Y'all all right? You good? Okay. Parts per million is abbreviated ppm. So now you've seen ppm. So 1 ppm is 1 part by weight or volume of solute in 1 million parts by weight or volume of solution. So tap water we do test as ppm because there's a lot of particles. So particles per million is a good way to do it. So in weight, it's weight over volume. 1 ppm is like 1 gram. So there's lots of ways to go about how you measure ppm. So basically what you're looking for is you have 2.2 grams of mercury in 750 grams of water. 750 grams is how many milliliters of water? That's an easy one. Yeah. Did you get it?
750.
Yeah. Remember that your gram and your milliliter, they're going to be the same when you're doing like for water, right? All right. So times 10 to the 6th. This is your million, 10 to the 6th, right? So then you end up getting that number, which gives you this number. So you can check your work and see, did you get 2.9 parts per million of mercury? Maybe you did, maybe you didn't. We got real close. There you go. All right. So how is a suspension different from a colloid?
Probably if they don't settle, right?
Yeah, a colloid, they don't settle, and the particles are much smaller in the colloid. They're going to scatter light. So suspensions will settle out if allowed to rest. Colloids typically will not. Suspensions contain larger particles than colloids. So milk, what you see, that the whey portion, the cream is going to go to the top in the milk because those lipids are much less dense. But the remainder of the milk, the whey and stuff that's left behind, that does not settle out. Those parts do not settle out. And your blood typically doesn't settle out unless you centrifuge it, as we saw, right? So blood's a suspension of different liquids and cells that have different densities. What's the best way to separate it? We just talked about it. Centrifuge it. Yep, in a centrifuge. Yep. So it's actually, I love, when we talk about it next year, we'll talk about it in biology, but it's all those layers have names. There's one called the Buffy coat. It's my favorite. Buffy coat. Why? I don't know. But yes, all those layers and those, when they separate it out like that, those layers give information, useful information to your physician about how much hemoglobin you have, how many red blood cells you have, if you have too many white blood cells. Like what does it mean if you have too many white blood cells?
Dead.
Not necessarily.
Your immune system is active.
Yeah, your immune system is active. Your white blood cells are your immune system. So if you have high white blood cells, it means that your immune system is fighting something. Now, that could be anything from a cold to cancer. So when you get high white blood cells, they tend to check you for those types of things because you never know. Like, and some people just produce extra white blood cells. My best friend found out the hard way. She produces like more white blood cells than the average person because they sent her to oncology and everything. And I spent days crying thinking she was going to die. She's not, she's just weird. But I already knew that. I don't know why I was, I already knew she's weird, y'all. My best friend's the best. Let me just tell you, we've been best friends since we were like 11 and 12 years old. This woman is one of the only people on this planet who can fall upstairs. I've seen it happen more than once. Like she fights gravity, and my best friend's she's a big girl. So when she falls up the stairs, she falls up the stairs, and and she'll fall down the stairs too. And she's just not graceful at all. And like the best was we were in like, I don't know, it was probably like ninth grade. And she went into my kitchen and she poured like a big old glass of orange juice. And she's coming back, and I had a tri-level house. So like the kitchen was on the middle floor, and then like the bedrooms are up here, and then the den was down below. And she's coming down to the den, and she did her typical whoop, and just this time she went down the stairs, but she threw the orange juice as she went, and it made this arc like a Jackson Pollock painting, like the whole wall. And my mother was like, I mean, it was just the whole wall. It was just splashed orange, and then it dripped down.
Oh.
It was bizarre. Like I'll tell you one more story. She's not here, and I can. But this is the kind of thing that would only happen to her, because this doesn't happen to normal people. So when I was in college, I went away for school. She didn't go to college. She stayed home and started working, and eventually built her own business that she ran for a couple years, which was great. But she was back in Virginia Beach. I was in Roanoke. And she called me one day and said, she's one of these people, she doesn't have like a huge vocabulary. So when she tells stories, it's really fun because she tends to add like sound effects and make up things. Like, and I was like, boom, and he was like, whoa, like that's how she tells stories, right? So she calls me and she's in an absolute shrieking panic because she had decided to thoroughly clean her room one day. You ever do that? Like you just gut your room, like your closet. She did it. She was cleaning her room, and she had spent the whole day cleaning her room, and she was done. So she said to herself, I'm going to go up to 7-Eleven. We have Waffle houses on every corner in Atlanta. In Virginia Beach, it's a 7-Eleven on literally like across the streets. It's 7-Elevens, right? So Chick goes to 7-Eleven because she wants to get herself a new pack of Marlboro Lights and a pina colada Slurpee, which they had at the time. The big ones, you know, like the big gulp is what it's called. It's like this big, right? So she had a little red Honda Civic hatchback at the time. And she also had a giant, stupid golden retriever. His name was Rocky, and he was darling, he was dumb as rocks. I mean, just a dumb dog. And he would get out and he'd run around the neighborhood, and he'd run around, and her dad would chase him on a bicycle. Rocky, kennel up. The dog didn't know what kennel up meant. He could care less. He was a big dumb dog, really sweet, just dumb. So he sat in the passenger seat of her car and go for a ride, you know, and off they went. So they went to the 7-Eleven right up at the corner of our neighborhood where we grew up. We used to walk up there before you could drive. So this chick goes in and buys her Marlboro Lights, and she doesn't smoke anymore, but she smoked all forever. She buys her Marlboro Lights, she's a 90s kid, and her big Slurpee. And she goes out the door. Now she had left the dog in the car, okay? Because it was summer. It was like August or something. I'd just barely gotten back to school, so it was hot. So she left the air on and left the car running with the dog in it, thinking nobody's gonna mess with my car, like giant dog, like he's a giant golden retriever. She comes out just in time to see this man in her driver's seat of her car starting to back up with her dog in the passenger seat, just looking so excited somebody new is gonna take him for a ride. So she does the first thing she thinks to do, which is to scream and throw the Slurpee at her windshield. And somehow she nailed it. Boom, Slurpee everywhere, right? So when I'm hearing the Slurpee, I was like, and he was like, so I threw it, and this is how she's telling me, right? So Slurpee explodes everywhere, all over her little car.
Oh my God.
And he keeps backing up because he's nonplussed. Who cares about Slurpee on the windshield? I mean, external wipers is gone, right? He didn't care. So then she does the next thing she can think to do, and this is why I'm saying this would only happen to Ducky. Her name's Shannon, but I've called her Ducky since we were 11, so she's Ducky. Ducky runs at the hood of her car and jumps on it, locking her fingers at the top of the hood at the bottom of the windshield. I told you she's a big girl. She's a big girl. She's probably a half-inch bigger than me and probably outweighs me by 130 pounds. She's a big girl. So she's holding on to the hood of her car, right? So this guy does this, right? He's jerking the steering wheel. So she's sliding around, and Drew's laughing because you can see her in your head because you know she didn't see her. So she's sliding on it, and eventually he flips her off and she rolls through the parking lot. You know, she just rolls. Meanwhile, the dogs. So he pulls away, and the cops come, and they take the report, and she's, oh, my dog. And a few minutes later, this lady pulls up with her dog, with Rocky, and says, I found him over there on Edinburgh. So this guy had gone around the corner and would just open the door and shove the dog out. So he was limping because he was old and it kind of hurt his hip, but he was all right. And he just was sore. But they found her car like 4 days later in an apartment parking lot where they had driven it. This dude had just driven it till it ran out of gas. Like they didn't use it, but they just joyride. And then they ran out of gas and they drove into it and they left it. But she was like, they had to fingerprint my whole car and it's covered in dust. And so, yeah, keep your best friend for life because then you've got stories. I've got plenty that are not appropriate to share with students, but yeah, she was the party girl. I was not. It was weird. Like we've been best friends since we were 11, but like when we were in high school, we went different ways on Friday nights. Like I would go out with Jason or stay home and she would go to whatever rager was happening. And then we'd get in the car Monday in the Mustang and I would drive to school and she would tell me all of the stories of her adventures. And I'm like, you are going to die. Like you're going to die one day. So yeah.
Video falling up the stairs.
I don't, it was like 1987. I don't have video of her falling up, but she literally will like never catch her footing and still moving up against gravity. It's impressive. And it's wild because like her daughter is super athletic, like so athletic that she's playing college softball, but not Ducky. Ducky's lucky she can walk straight most days, but she is my ride or die. You know, everybody should have that ride or die. Love her to bits. She's a goober. Okay, so back on topic. What is a molarity of a solution containing 0.15 moles of potassium chloride in 350 milliliters of solution? So how do we figure this out? So we have to take our 0.15 moles of potassium chloride and divide it by our 350 milliliters of solution. And then we're going to multiply by this conversion factor Y because molarity is moles per liter. We need liter, not milliliter. And we end up with 0.43 molarity. Y'all got that one? We got that one. I tell bad chemistry jokes because all the good ones, this is my favorite, are gone. That one's my favorite. I had a student years ago she and her mom make like t-shirts and vinyl things, and she made me a wine tumbler with this on it. And I'm like, this is the coolest wine tumbler I've ever received. So nerdy. I love it. Yeah. All right. So if you want, you've got a little extra time, not too much, about 20 minutes probably. If you want to work on that lab while you're still here, you can. Or if you want to split, you can. James, question?
Check to make sure I uploaded my thing to the right place.
Oh, did you already do your meme? Okay, so let me look. I'll show everybody where it is so that everybody sees it. It is. I want to make sure I'm sharing screen so that Andrew sees this because he's not here. All right, so you're gonna do like always. You go to all the links. It's always slow when it's hooked up. There you go. So you should be able to find it when you get into the forum. It'll be under the one that says chemistry all, which is, I think the color for that one's white. And it's under a heading that says memes. So this is labs. So you want to come out of labs and go back to categories here. And no, thank you. Go away. Oh, you can find it right here on the side too. See it popped up there? So there we got James. Oh, what did he do? What did he do? I'll count that. That's great. There you go. When your teacher makes you listen to science puns, but you're just a chill guy. I'll take that. That works. That wasn't one of the ones from the slideshow, but it's pretty good. I'll take it. So yeah. So that's the kind of thing you want if you want to get to 2 points. Yeah.
So we have to use a joke from the slideshow, but make it in a different
Yeah, just make your own meme. Yeah, don't copy one that's in the slideshow, but make your own meme or your own joke or your own pun. But yeah, And find your ride or die if you don't already have that person. Cause I tell you what, having somebody that's been through like high school and like college and marriage and childbirth and all that, be the same person, it's invaluable. Yeah. And I can say anything to her, she can say anything to me. Everybody needs that person, right? I'm laughing at her, but she would be laughing herself right now. She's the one whose mom died this fall. Then I went to Virginia for that weekend. Yeah. But yeah, everybody needs, if you don't have them, fun for sure. Flips. So yeah, if you've got extra time, you went on your ride, work on your lab. And I'll put that back up. Did you think you were dying?
Yes.
Oh no.
What?
You're waving.